So that last value of energy for that calculation that we calculated is 11,400 nanometers, because it was a wavelength, right?
Yeah.
It's the correct value. The answer at 11,400 nanometers, you are in the infrared. It's just that the little Chapman cycle is called, that said UVA does this, UVB does this, UVC does this.
Okay.
For the ozone degradation, it said UV.
Okay.
But turns out that it really interacts with infrared. That doesn't mean that UV is not involved. It might be catalytic in some process. And we're going to talk about that today. That these reactions are not direct. They are indirect. And there's a few things involved along the way. So let's look at mechanisms, because there's a couple written in the book of ozone depletion. So the one that we mostly need to care about, there are things that we know are damaging, there are things that we know that we want to limit, and we have a sense of what the mechanism of that depletion looks like. We'll show you a couple of different variations on it. Okay. In the sense of chemistry in general, organic chemistry is where we mostly use this word. What's the mechanism?
It's the process through which a molecule or chemical or a solution, I don't know how to explain that, undergoes change.
Okay. So the process of change. So a reaction then. Right. Why don't we just say reaction? What's the difference between a reaction and the mechanism?
You're showing where like charges go.
So in the mechanisms that we draw for organic chemistry, we're very explicit about where reactions start, where they finish, what's causing the reaction to perform, what's being attacked, what bonds are being broken, what bonds are being formed. But mechanism in a general sense is simpler than that. It's just the step-by-step part of the reaction. So if I show you, here's a reactant arrow, here's the product, that's just a reaction. But if I show you step-by-step how we get there, then that becomes a mechanism. So mechanisms are the step-by-step analysis of reactions. And if you've had organic chemistry, if you've not had organic chemistry, it doesn't matter. But we did use a word last week, radical. And if you've had organic chemistry, you know that we represent the step-by-step mechanism of how radicals perform what it is that they're performing chemistry-wise in a slightly different way than we do all other regular acid-base type reactions. The radicals are usually written as a line-by-line process, whereas the kind of acid-base reaction is a flow. I start here, the reactions flow there, and then they cascade and they do something else. Okay.
Propagation, initiation, and...
Yeah, so radical reactions have 3 steps. They are radical propagation, radical initiation, propagation, and termination. Radicals being very, very reactive. There's a balance to be had with things. When you are incredibly reactive, that means that you don't have any specificity. You'll react with anything. And when your number of options gets open because you yourself are so very highly reactive, that means that lots of things in the universe get to knock you out. Okay. All right, so let's look at a couple of things. Our book does this over page 20 and 21. I would have liked them to stack them on top of each other. They don't, but that's okay. And our book, I'm sure this is environmental chemistry speech, shows us two variations of the same theme. I'm going to go with the first one, mechanism 1. Mechanism 1 does this. Before I write it on the board, there's a couple of abbreviations that we use in chemistry that, that might come up. They're generic. They don't represent anything in specific. If I want to tell you that I'm looking at a metal, I just write M. There is no M on the periodic table. There's no element M. M just means metal. R means some carbon-containing organic group. And I'm not going to specify any more than that. I'm just going to let it be. It could be one of a billion different carbon, hydrogen containing groups. And then X. X usually means a halogen. But it's kind of, we associate it with non-metals first. So non-metals, I'm going to be so incredibly generic. Like back to chemistry 1, where we say, hey, metals undergo oxidation, they lose their electrons, non-metals gain electrons by reduction, and then M plus meets X minus, and they make an ionic compound. Okay, this is generic. Metal, non-metal. Most of the time, X is going to be a halogen. Halogens are group 7 gases. They're the fluorines, chlorines, bromines, iodines of the world. Fluorine and chlorine are gases. Bromine is very heavy. It's a volatile liquid. It's very easy to put it into the gas phase. But iodine's a solid. It does make a vapor. It sublimes. We're probably not talking about iodine. Okay. Just for generics. Here's how this is going to go. Some currently unnamed non-metal elements. Probably a chlorine. The big one that we're going to spend time assessing the environmental impact of is chlorine. But it doesn't have to be. It could be a couple of other things. There are a number of other naturally occurring things. And ozone are going to come together. Oh, we didn't do the Lewis structure.
Yeah.
That just reminded me. And we're going to make some oxide of my non-metal. Well, there's a whole bunch of non-metal oxides out there, and we can think of stuff that's like what we consider naturally occurring. We have nitrogen oxides. Anyway, but there's stuff that we haven't seen before because we haven't done environmental chemistry before. It doesn't really show up anywhere outside of this field. And then the thing that's left over gets to be dioxygen. This is all happening in the gas phase. Does our book contain state symbols? No, it doesn't. Should we put them in? Probably. I mean, we're doing this in the gas phase, right? Let's just go pencil these in. state symbols are not subscripted. They are written in lowercase parentheses behind the reagents. And we have solid, liquid, gas, and AQ for dissolved in water, aqueous solution. Okay. All right. Well, ozone, we kind of prodded at earlier. Not a stable molecule, high energy molecule, and is going to break apart, given the opportunity, to make a very stable molecule. Okay. And then we see something that might be a little bit familiar. I'm going to take this thing that I've made, it's in the gas phase, and I'm going to react it with just elemental oxygen, with monatomic oxygen. So that's actually been on the board, but it's not, we should probably reiterate, because if you listen to what I say during Chemistry 1, I tell you over and over again that this doesn't exist. Only this exists. This doesn't exist. Well, it's a high energy molecule. It can exist, it does exist. We don't need to consider it at ground level, but in the atmosphere, yes we do. Okay? And then that gives us this. Okay. It's a two-stage reaction. So this mechanism that we're going to call mechanism 1 goes by 2 steps. Let's call step 1, 1, and call step 2, 2. If we do the simple math of this, simultaneous equations, the arrow is an equal sign. Everything that's on the left gets added together. Everything that's on the right gets added together. So if we just add line 1 to line 2, I get X plus O3 plus XO plus O makes XO plus O2 plus X plus O2. So this is line 1 and line 2, and we would call this the overall reaction. It's a 2-step process. These are what we call elementary steps in order to get to the overall step. Let's write that. Because if it's mentioned in the book, I haven't found it mentioned yet. But these are what we have previously known as elementary steps. Okay, and at this point, you might have noticed something. What are we going to do?
Cancel some stuff.
We're going to cancel a whole bunch of stuff. Okay, so the way that we do this is, here's my equal sign, there's my arrow. If you are on both sides of the equal sign, you got to go. So X, does X appear anywhere other than where I'm pointing? Yeah, there's one over there. So that one and this one cancel each other out. O3, this is the ozone itself. is there any other ozone on the line? Nope, so we get to keep it. XO. Again, X is some non-metal. We haven't decided what it is yet. That cancels. And then O. Now I get to keep that. Which means I'm done. But just in case you made a mistake, you go and you count this O2 and that O2. All right, so overall, my reaction is ozone plus atomic oxygen makes 2 molecules of oxygen. This is what we call comproportionation. Oh, it's a word that I wasn't expecting to use in this class. This is a big thing and a little thing combining together to make a medium thing. The reaction in the other direction, if we started here and moved that way, this would be a disproportionation. That's much more commonly seen in general chemistry of, I'm starting in the middle, O2, and I'm making an O3 and an O, making something higher on the list and something lower on the list. Disproportionation. This way, comproportionation. I'll write it over here, because it absolutely is not in the book. Dis and con, I'm fairly confident it's comproportionation, not con.
Mm-hmm.
But we might want to check before it's on the board forever and glorified in video.
When we add into overalls, it doesn't matter which one we write first.
No, you could put these in any order you want. Yeah. No. There was a point when I started writing that I thought, do I even bother putting X first? Because what's the message here? The message is ozone. And I was going to start with O3. Our book starts with the X, so I kept it the way that it is in the book. Doesn't matter.
It's common.
Okay, so this has us pondering about what are the things that I've removed. I've removed 2 things. I've removed XO and I've removed X, and they both serve different purposes. What are they? Let's look. Let's do them not in the order that they appear on the page. This guy. So XO is produced in reaction 1, but then consumed in reaction 2. You make it here, made, and then it's consumed here. It's the product of line 1, but it's a reactant in line 2. So it doesn't show up in the final answer. And if we didn't know to look for it, we would never see it. Because what is the reaction, not the mechanism now, what is the reaction of ozone depletion? This guy. Ozone meets monatomic oxygen and makes 2 molecules of dioxygen. But we know that that's not true. Because if I put these two together in a flask, shape of the flask, don't get this. This is involved but doesn't show up. Do you remember what that's called?
Intermediate?
That's a reactive intermediate, yeah. This is what we call a reactive intermediate. And reactive intermediates are made in one step and then consumed in a later step. You have to make them first and then consume them. So they don't show up in the overall. They don't show up. And yet, if they weren't there, this reaction doesn't go the way that we see it go. So XO is a reactive intermediate. Okay. What about, I need to,
Different
like
color?
another different
Oh wait,
color.
I have a bunch.
If you had a blue,
I
blue
do.
would actually work.
I got some blues.
Because I've already got red and green on the board.
Oh no, I took them all out.
It's fine.
Just kidding.
I'll do it.
They're actually at the board over there.
It's fine. Let's look at what the role of X is. X is consumed in one, but X is then produced. I'm going to say regenerated because that's the word that we use for what this particular thing is. What does this make X? Here's a clue. If I take X away, does the reaction work? No. The reaction does not work in the absence of X. If I take the X away, the reaction does not work. And yet, when I look at the end, X is still there. So it is vital for the reaction to progress, and yet it is not consumed by the reaction. It's there at the beginning, it's there at the end. That's why it doesn't show up in the overall, because it's there at the beginning and it's there at the end. But the reaction doesn't work without it. A thing that the reaction needs in order to progress, but that thing does not get consumed by the reaction, is called a... Kick yourself.
Oh.
It's a catalyst. So, the message here, and it's going to become apparent when we read further into the chapter. In fact, the next chapter, the first chapter, this chapter is the science of the ozone, and then the next chapter is the historical record of what we've done and what we've put up there. And one of the things that we've put up there is just straight chlorine. We didn't mean to. We took every every attempt that we could think of to not put it there, they got there anyway. That's going to be a chlorine, and that chlorine will catalyze the depletion of ozone and then pop out at the end. So it doesn't show up. Okay. Now, how did that get there? This doesn't just show up on its own either. That has its own line that is not part of this mechanism, unless you really, really want to be complete. But there is a subset here, and we put it on the board on Thursday, but that comes from ozone. No, that comes from dioxygen. The dioxygen gas will turn into two monatomic oxygen gases if you hit it with ultraviolet light. That's an endothermic reaction. Okay, this is the generics then for our first mechanism. And the book, well, the book knows that we're going to eventually blame chlorine, and before it says, okay, we're not going to exclusively blame chlorine, it says there's a natural way that this happens, and that there is a natural culprit, and that culprit is nitrogen monoxide. So let's do this. Mechanism 1. Yeah.
Is it possible to have something produced twice?
Yeah. Yeah. It just, if you have something produced in line 1 and line 2, or produced multiple times, they just all add up together. Yeah, 100%. Okay, so we're going to call X. Our book doesn't call it the culprit, but let's call it the culprit. We know what a culprit is. What's the root of the word culprit? It's obviously Latin, right? We have to look at the etymology of culprit. N-O, which has...
Culpa, fault.
Yeah, so mea culpa is my fault. Culpa
Yeah.
is fault. The culprit is the person who is at fault.
Mm-hmm.
The naming system for nitrogen oxides could be easy. Dinitrogen oxide, nitrogen monoxide, nitrogen dioxide,
Mm-hmm.
nitrogen trioxide. However, people got to it before we did, and that's why there are things called nitrous oxide and nitric oxide. Ic means a particular amount of oxygen. Us means one less oxygen than that. So there are things out there that are nitrous oxide, and there are things out there that are nitric oxides. If in doubt, use the systematic name. This is nitrogen monoxide. There's one nitrogen and one oxygen. Hey, this is going to be our culprit. It shows up this way. We're going to start with dinitrogen oxide, which is known as nitrous oxide, and it's going to react with monatomic oxygen and makes 2 NOs, so it's got to be down the side. This has to be a very, very low yield reaction, because thankfully I've left space above it. But if you take N2O as a gas and a single atom of oxygen as a gas, okay, here's what I want you to do. I want you to go all the way back to like the 3rd week of General Chemistry 1 and say, I'm learning to balance equations from the very, very beginning. How many nitrogen atoms are on the left-hand side of this equation? 2. And how many oxygen atoms are on the left-hand side of this equation? 2. And so one of the possible, feasible answers to how this would rearrange itself has to be and N2 is 78% of the Earth's atmosphere, and O2 is 21% of the Earth's atmosphere. Because that's exceptionally stable, and this is really highly stable. So this has to be the dominant recombination of nitrous oxide and monatomic oxygen. Has to be. But occasionally, something's going to go a bit wrong. If it goes a little bit wrong, you could just split those apart and make two of the same thing. To make 2 nitrogen monoxides. Okay. This is going to be our culprit. Our book says something, let me have a quick look. One important natural version of X, our culprit, is nitric oxide, NO. So this is dinitrogen. I'm gonna go the systematic way, right? So this gets to be dinitrogen oxide. This one's called nitric oxide. And this one is called nitrous oxide. That's the old-fashioned way of saying it. It hasn't gone away. And us means less than ick, the same way that ite means less than 8. The nitrites have less oxygen in them than nitrates. Nitrous has less oxygen in it than nitric. But again, if in doubt, just call out the number of atoms by number. Okay, so we could make a very small amount of this by kind of cosmic accident. It says it's produced when molecules of nitrous oxide rise from the troposphere to the stratosphere, where they eventually collide with oxygen atoms that are in their excited state. Okay, so not only has it been separated from its parent molecule, it's now in an excited state, and we show excited states a couple of different ways in chemistry. We either just put a little asterisk there, or we put A dagger, that's not a plus. This is a plus. A dagger, it's longer. Or sometimes like a double dagger. I think daggers can be confused for pluses. So asterisks work a little bit better. So this is in its excited state. Remember, ultraviolet radiation works on the level that that wavelength of energy impacts bonds and pushes electrons from where they are in their ground state up to an excited state. Should sound familiar to people who are in several different classes at me at the same time, because we're saying this thing in multiple different classes all at the same time now. That you can promote electrons from one place to another place inside the molecule by ultraviolet light. Okay, so that's its excited state. The non-excited state is called the ground state. All right, so we're going to make this, and then this is now X. So here's X, and it's going to react with ozone, and it's going to make what? We said XO. So NO becomes NO2, nitrogen dioxide. NO2. And then the NO2, which is my XO, reacts with what? And makes X. Nope, X. And O2. So we're going to write everything out. NO in the gas phase plus O3 in the gas phase plus NO2 in the gas phase plus O in the gas phase makes NO2 in the gas phase plus O2 in the gas phase plus NO in the gas phase plus O2 in the gas phase. And then you take out the red pen. Gone. Keep. Keep. So overall, this reads as O3 plus O makes two O2s. And presented with this, you have none of the information about what just went on. Because the information about what went on was, wait a minute, I had this guy. What is he?
Nitrogen oxide.
Okay, and what's his role here?
Oh, he's a catalyst, right? With O.
Yep,
Yeah.
yep. He's the catalyst. And then this guy, this doesn't show up in the overall reaction either. What's his role?
Intermediate.
That's the reactive intermediate. So this guy doesn't show up in the finished balanced reaction, the catalyst, and this guy doesn't show up either. Which is why we have mechanisms in the first place. Because the mechanisms show us what we need to know. This is the reaction. This is the overall reaction. It tells us very little about how the reaction works. Mechanisms tell us how the reaction works. This just tells us what we got. This tells us the stoichiometry of one of these and one of those makes two of these. But it doesn't tell us much else.
Do we have to show the restrict where we cancel it out?
If asked to, sure, but you could cancel at this level and just go, no, look, and then this one, no. Okay, one of the things that I was kind of hoping for when I saw that this topic was in the book was this is a really good opportunity to talk about the kinetics of mechanisms that occur in two steps. Because when mechanisms occur in two steps, they're going to be dependent on only one of the steps. Because it's just not feasible that both of these reactions occur at exactly the same rate. One of them has to be faster than the other. It's just the probability means that one of the reactions is fast and one of the reactions is slower. And in the world of kinetics, now the book does talk about kinetics, but it just gifts us the numbers. It doesn't show in any way at all how we would find those numbers. It just says, hey, here's some numbers. This is how it works. And that's a missed opportunity, but it's okay. It's okay. So kinetics tells us things about the rate of reaction. Okay. What is a rate?
Something over time.
Yeah. A rate, if we're going to define what something is and then we use a word that has to be defined itself, a rate is something measurable divided by time. In chemistry, in the gas phase, this could be collisions per second. It could be molarity per minute. That, hey, at the beginning of the reaction, I had this concentration of reactants, and at the end, I have a diminished concentration. And if I know the time that I started and the time that I ended, I can map my change in concentration to the change in time. That's a rate. Okay? Because they're gases, how else could we measure them? Gases can be measured.
Pressure.
Okay.
I was getting it.
Because PV equals nRT, the number of moles of a gas is reflected in its pressure. So I could map the pressure change versus time. And that would tell me something about how much I started with and how much I ended with. I can turn pressure into a number of moles. Okay, so kinetics tells us about the rate of reactions. When looking at a reaction, what do we investigate? What can we get information about? If I want to know how to make this reaction go faster or slower. What options do I have to vary?
If we're going on PB,
No, just in general. It's basically
concentration
of
of the concentration of mold, like mold.
okay.
Yeah.
There's something so fundamental here, so obvious that it can't be seen. It's okay that you can't see it because the answer is just so obvious. The reaction has two sides, the reactants and products. Which one of those sides is doing the reaction? The reactants are doing the reaction. The products aren't. The products have already been made. So if you want to assess whether a reaction is going to go or not go, and you want to assess how fast it's going and what effect changing something will have on this reaction, you only look at the reactants, because it's the reactants that are doing the reacting. The products, depending on your point of view, have already been made or haven't been made yet, is probably the better way of seeing it. The products don't have anything to say about the reaction speed because they have not been made yet. Okay. So we, when we do a kinetic study, we investigate that from the reactant side. If I want to know what the dependence is of this reaction, I see that ozone is a reactant. And I give my reaction a bit more ozone, a bit less. And I see, hey, does that make it go better? Does it make it go worse? Does it make it go a lot better? Does it make it go a little bit better? Okay. And we have those situations where we have a couple of different types of behavior. We call those first order, second order, and zero order in chemistry. That a zero order relationship means that when I change the concentration of a reactant, nothing happens. Nothing happens at all. The reaction rate is unchanged by something that I do to the reactant. First order is whatever change I make to the reactant, the same thing happens to the rate. That if I double this, the rate also doubles. That if I increase this by 5, then the rate also increases by 5. And then the second order, and the second order is that if I increase this by 2, if I double this, then my rate goes up by 4. And if I increase this by 5, then my rate goes up by 25. That the effect that I see on the rate is the square of what I did. If that's in our book, it's hidden from me. I haven't seen it yet. Okay, so I've said it out loud. I would like it to be in the book. It's not, and that's okay. It's okay. We're gonna spend more time talking about impact than science. That's okay. Okay. Now, let's get back to this. These are elementary steps. Both of these. This is the overall. And one of the things that happens in the study of kinetics, how fast a reaction is going or not, is you can learn absolutely nothing from looking at the overall reaction. You can tell nothing. If you want to know, does this reaction go better or worse when I change the concentration of ozone, you have to do it by experiment, which is why we do those kinetic studies in chemistry of, I'm going to take this reaction and I'm going to vary this. I'm going to keep that one constant. I'm going to vary this and see, is there any effect? That's because this is a lie. Right? It's not a lie, but it's not the whole truth. This is a bigger picture. It tells us there's whole bunches of things going on in this reaction that you cannot see because they've all cancelled each other out. Which means I cannot gain meaningful kinetic information from the overall reaction. I have to look at the elementary steps. And in an elementary step, something really powerful happens. The overall rate of any elementary step is the concentrations of its reactants. You don't have to do the kinetic study. If these are true elementary steps, then their rate law just follows whatever the reactants are. And we only follow what the reactants are doing because it's the reactants that are doing it. Okay? So, let's build a rate law. A rate law says this, that the rate of the reaction is equal to some value, K, which is called the rate constant. And the rate constant is, it's not like the gas constant where it's a number that gets used for all reactions, all processes, all the time. It's not a constant like the speed of light, which is used to describe all electromagnetic radiation. This belongs to this reaction at that temperature. And if you change the temperature, you change the number. This shouldn't even be a constant. It should be a coefficient, right? This has to be at a given temperature. If you don't state the temperature, your rate constant is invalid. And one of the things that we're going to do, and our book is actually doing, is if this is the amount of ozone that I deplete at 25 degrees Celsius, how much do I deplete at 50 degrees Celsius? It's the Arrhenius equation. They do it slightly differently than the methods that we do in general chemistry, but there are two forms of the Arrhenius equation it uses well. Okay, so this is line 1, and this is line 2. For line 1, rate is equal to K, concentration, square brackets means concentration, of NO in the gas phase multiplied by the concentration of ozone in the gas phase. And for line 2, the rate is equal to K NO2. Oh, I didn't finish this thought.
Oh.
Rate is this right here. Means concentration. Of reactants. Okay. So I have two back-to-back reactions. I can find the missing information just by having some of the information. This might be observed, these might be measured, this might be given in a textbook. I might have that information from a previous coworker that worked this out, and I'm putting today's numbers in to my equation, okay? That for, this is a big, big asterisk here. This only works for elementary steps. Not the overall reaction. Now, it might be true that the overall reaction is rate equals K O3 times O, but I would only be able to prove that experimentally. I can't look at it and know. For an elementary step, I can look and know. Okay? The elementary steps are the step-by-step part that build the mechanism to give me the overall reaction. I cannot look at an overall reaction and get meaningful kinetic information out of just its stoichiometry. But I can at the elementary step level. Okay. One of these those steps is slower than the other. Whichever one is the slowest step is called the rate determining step. And in any multiple step process, this one only has 2 steps, but it doesn't matter how many steps you have in your process. If you have a multi-step process, one of those steps is slower than the others. That's the one that all the math is going to hinge on, because what can we think of in real life where you do something and then you do something after it, and one of those steps is really instantaneous and the other one you have to wait for. I mean, there's a billion analogies. I just can't think of any.
You have to pay your taxes. You have to pay out taxes every paycheck, but then you have to wait for a tax return to get one.
Okay.
It's really only, it's a very small amount of people that that applies to.
Okay. Well, it takes me forever to do my tax returns, so it doesn't look. Things like, this really bizarre thing happened on Friday. Driving home in traffic Friday at like 5 o'clock, and there was a car in front of me, and a car in front of that, and a car in front of that, and a car. There's hundreds of cars, and there's a person, and I heard somebody honk. They couldn't possibly have been honking at me because I'm stuck in traffic also. And about 10 minutes down the road, the car that was behind me turns right, And the woman makes a face at me, like, it's my fault. I can't drive through the car that's in front of me. We're gonna get to the same red light at exactly the same time. But this is the deal, okay? So this is a way that rate determining steps work. Here is, oh, not very good at drawing. What do churches look like?
There's a cross outside of it.
They have a steeple with the clock tower. And then here's your house. And the groom goes in one car and the bride goes in another car. Okay, there are two scenarios. One is that the first car zooms off and gets there. And then they wait for the slow car to get there. Or the first car is the slow car, and the other car behind it is exasperated. Why don't you go any faster? Because as soon as you go, I can go. If you would just go, I would go. And they both, this guy has to wait until the slow one gets there. This is the rate determining step. Doesn't matter kinetically how fast the fast step is. That's immaterial. It only matters how slow the slow step is. Okay? So if we know which one of these is the slow step, then I know the rate law for the overall reaction. And when we look at the two possible answers, the rate law is either this one or that one. Neither of them have one of the reactants that shows up in the overall reaction. This one says you have to have O in your overall reaction. Oh no, I did it wrong. I did it wrong. I did it wrong. I did it wrong. Yeah, that's wrong. We fixed it. Fix it in your book. Just force a habit.
Yeah.
Yeah. Just like, but neither of them have both the ozone and the monatomic oxygen. So, yeah, strange. So whichever is the slow step, that becomes the rate law. So I need space, don't I? Because this is a takeaway message. That the rate law of the rate determining step, that is the elementary step, is equal to the rate law of the whole reaction. Regardless of what it says in it. And our book tells us that it's the first one, that the overall rate is the top one. This guy. And it throws some numbers. It doesn't make you derive those numbers. It just says, hey, if your rate constant is this value and these are your concentrations, then what is the rate? You got 5 minutes. You want to do it? Mm-hmm. Okay. Because it's written there in the book, but it's kind of in text, not on the board. Okay, so let's do it, and then we'll pull up the others. So we're going to decide that line 1 is the rate determining step. By measurements, we're going to measure this reaction, and we find that line 1 is the rate determining step. What book says. Let's just use the numbers that are in the book. The K is 6.5 times 10 to the negative 15, small, molecules per cubic centimeter. So a cubic centimeter is a milliliter. And if I want to say per cubic centimeter, I can either say per cubic centimeter, or I can say this. And like we said, if you don't tell me what the temperature is, there's not a reusable value of K. So this is at negative 50 degrees Celsius. Not comfortable with that number being in Celsius. We're not going to use it. It's not part of the calculation. Still, when it does become part of the calculation, there's no way that we're keeping it in Celsius. Temperatures that are used in calculations have to be in Kelvin. What is negative 50 degrees Celsius in Kelvin? Just for the sake of doing it on the board.
23?
273 Kelvin is 0 degrees Celsius. That's my conversion factor. All right, so K is this. If I know the value of NO, concentration, and I know the value of O3, concentration, square brackets means concentration, then I could find the rates. NO is 1 times 10 to the 9. That's a billion molecules per cubic centimeter per milliliter. It's actually not a big number. 1 billion molecules per milliliter. Multiply that by 1,000. That's 1 trillion molecules per liter. When Avogadro's number is 6.023 times 10 to the 23. So, yeah, this is still dilute. Oh look, there's 1 billion molecules. Yeah, but you're dilute. You are still dilute. Okay.
The 223 Kelvin, it's a temperature for all of them? Or
Yes. Yeah, has to be. Okay, so the rate is this number multiplied by that number multiplied by that number. Again, this is in the book, but they write it in a paragraph. They don't write it out like we would want to see a calculation with the numbers stacked on top of each other. So this just gets to be 6.5 times 10 to the negative 15. I'm going to call that, I can't call it moles, because that means moles. Molecules per milliliter. the time in here.
I'm missing, there's something I haven't written down. Yeah,
Per second. Per second. It's a rate. Has to be divided by time. Multiplied by 1 times 10 to the 9 molecules per milliliter. Multiplied by 3 times 10 to the 12, 3 trillion molecules per milliliter equals. I've just multiplied those numbers.
Whenever we write it out, do we have to put the units? Or-
You keep the units in the calculation just to keep yourself on track to make sure that you're doing the right thing.
yeah, we just find a number and then make that number make sense.
So let's fix this because I've said this wrong more than once. It is per molecule, per milliliter, per second,
Okay.
which makes these go away. Well, it makes one of them go away. That's the trouble with units in kinetics and in I suspect that our book has got this one wrong. Per molecule, per centimeter cubed, per second. Okay. Because there are two concentrations here, and because the units have to cancel each other out, that's not the right unit. These are not the right unit. But the book's trying to just come to a point where it's not got it. This is a second order overall reaction. Oh no, that is right. It is right, isn't it? Because the first ones,
Oh, wait.
yeah, the first ones cancel. This set cancels, and then it leaves that behind. No, it's correct. I
So you get-
withdraw my whispered comment about the book being a mistake. This one cancels that one. This one cancels that one. This one comes through, and it gives us an overall molecule per milliliter per second. It is correct. What's your value?
1 point, so 2 times 10 to the 7, or if that's rounded up, it's 1.95, but I can't do
Okay,
the actual.
we'll write that down as 1.95 times 10 to the 7 molecules per milliliter per second. It does work. Per molecule, molecule goes away. Per milliliter, milliliter goes away. Per second stays. Molecules per milliliter stay. Yeah, it is correct. And because we're only allowed 2 significant figures in this calculation, our book has rounded that up to 2 times 10 to the 7. Okay.
Thursday, we'll look at the other mechanism. We've done all the hard work, hard lifting with this one.
There's another one that has a third step. And then we'll go look at what all the fuss is about. What did we do wrong? And what have we tried to fix in order to make ozone depletion be a thing of